Welcome to this RISC-V Summit panel. I am Ann Mutschler, Executive Editor for EDA at Semiconductor Engineering. During this panel, we're going to attempt to answer the question, is the RISC-V verification ecosystem ready for the coming innovation tsunami? The historical assumption often quoted is that verification represents 60 to 80% or more of the SoC project effort in terms of both cost and time, if we're talking about mature mainstream processor IP cores. The processor IP business model was based on the leverage of one size fits all over many projects to offset upfront investment. If the innovation with RISC-V increases the verification work on each design, does this affect the bandwidth across the industry to support this shift in the verification responsibility? It's an interesting time in the industry with RISC-V and what it offers to all SoC developers, which is the opportunity to optimize a processor design either as a new implementation or modification of an open source or commercial core. Before we dive into the topic, some introductions. Our first panelist is Mike Thompson, Director of Verification at Open Hardware Group. Thanks for being with us today, Mike. Could you share a bit of your background and what you're working on with RISC-V today?
Sure, thanks, Ann. Once again, my name is Mike Thompson. I'm with the Open Hardware Group, and I've been doing functional verification of pre-silicon designs for more than a couple of decades now, and the last several years in embedded processors, and the last year full-on focused on RISC-V. In fact, we just achieved a milestone with the first RISC-V core at the Open Hardware Group, which we call Core 5, and it's on GitHub. Go get it.
Great. Our second panelist is Nasrullah, Senior Director at Sci-Fi. Hello, Nasr. Thank you for being here today. Would you mind sharing some of your background and your involvement with RISC-V?
Hello, everybody. My name is Nasrullah. I'm in Sci-Fi. I'm responsible for the performance architecture group of Sci-Fi. And there I'm responsible for everything to do with performance analysis, performance verification, performance optimization for the next generation Sci-Fi RISC-V cores. In my past experience, I've done this for 3 decades in all aspects of performance for various companies.
Great. Our third panelist is Simon Davidman, CEO of Imperis Software. Welcome, Simon. Thank you for participating today. Could you possibly give an overview of your background as well as how you are involved with RISC-V today?
Sure, Anne. Yes, and thanks for having me here on this panel. So yeah, I've been an engineer and I guess software developer for almost 4 decades, actually. From engineering through to running companies. I was involved with the development of Verilog and HDLs in the 80s and 90s. And I founded, the company I founded before Imperis developed System Verilog. And after that, I became a VP in Synopsys after that acquisition. And then I created Imperis. And Imperis is a small company. And the team is all focused on EDA and SoC verification. And we worked in processor companies and EDA companies. And since 2017, we've been involved with RISC-V. And the topic of this panel is processor hardware DV, and it requires much more effort and tools than simple IP integration verification that the industry is used to. It requires, we believe, highly configurable envelope models and very configurable simulators that are only available from companies such as Imperis. And we provide advanced solutions in the verification of RISC-V, and more than half the companies taking RISC-V to silicon use Imperis solutions.
Great. And rounding out our panel today is Steve Richmond, Verification Manager at Silicon Labs. Hello, Steve. Thank you for being here today. Could you also share a bit of your background and explain how you are looking at RISC-V today?
Sure. Thanks, Anna. Thanks for having me on the panel. I am the manager of the Central R&D Verification team at Silicon Labs. Our charter is to develop verification methodology and execute verification on multiple advanced IPs, and included in that is our RISC-V core roadmap. I'm also the co-chair of the verification task group within Open Hardware. So we've been very heavily involved these last few months delivering our first core, as Mike has mentioned, in the test bench architecture, verification, test development, and testing. And we're very excited for the release of our very first core.
Great. Thank you so much. Thanks, everyone. So we're going to get right into some questions. Just a reminder, there is a text chat. Feel free to enter your questions there. And then also there is a speaker session where you will be able to interact with the speakers. Please watch for that in the summit schedule. So first of all, let's just go quickly a little bit and talk about how are RISC-V design innovations driving new design verification advances. Nasser, can you talk a little bit about that?
So I'm going to focus a little bit on a few aspects of verification that's on the sidelines here. And we do a lot of functional verification, but with RISC-V going everywhere in the ecosystem, the question of performance verification has also become very important. And that it gets harder because not only do your engineers have to know functionally how it works, but you have to have a set of engineers who understands, well, how long would it take and what can we do to make it better? That is very difficult to do. For performance verification, the second problem that comes in, unlike functional verification, where you can focus on a lot of very hardcore, low-level tests, with performance verification, you have to start worrying about application level programs coming in and how they all interact, all the pieces interact together. And then it becomes a problem of being able to use just a Verilog simulator or something like that. And you have to start looking at other options to do this. We have in Sci-Fi, we have a very high-end performance model that we do a lot of modeling work on. But once the RTL gets built and the complex interactions start working, you have to go to something that can mimic the entire system. And
Great.
Emulation tends to be what we have to use. And RISC-V has got some innovations in that. FireSim is a tool that was developed by UC Berkeley that is chisel-based, that is a very fast emulation solution. And we have been using it successfully in Sci-Fi to build our systems way before tape out and actually run full applications and OSs on them. And that has proven to be very useful. And to get to Simon, it's still an emulator. So you want to be able to mix and match it with simulation because you can't run everything in emulation. And to do that, you have to talk about mixing and matching in a hybrid fashion, a simulator with an emulator. And Simon is the expert in that arena. So those are the innovations I think that's necessary.
That's great. Thanks, Nasser. Simon?
Yeah, I mean, I think that the question, just to go back a little bit to the question, is that is RISC-V design innovation changing verification and driving that? And I think absolutely it is because it's now about a lot of people have to verify the processor, whereas before they weren't. And verifying a processor, whether it's the functionality or the performance, is something very new. It used to be done internally in the Intels, the ARM architecture licenses, MIPS and people, and it was all very proprietary and very homegrown. And those companies had huge resources to do it and developed a lot of very, very smart stuff and an internal proprietary solution that wasn't very public in there. And I think that now there's this whole verification ecosystem coming for RISC-V, with companies getting involved. I mean, in the formal space, Axiomize and companies like your one's of course. And then there's companies like Cadence with verification IP, Mentor and Synopsys doing emulators and simulation. So I think that the process of DV is changing dramatically. And I think that the ecosystem is evolving to help it. I mean, from an empirist point of view, we've developed, free tests and given those away. We took our simulation technology and developed some free simulation to help in the compliance group. And we now are focused a lot more on the hardware DV, producing these very complex sort of step and compare verification environments so people can really get high quality cores in a verification environment that only used to be available in the Intels and ARMs and like that. So I think that the challenge of RISC-V is challenging the EDA and the verification ecosystem to come up with new and better solutions to help them, because now it's not just one or two companies have to do processor DV, it's everybody. So absolutely, the RISC-V is driving new advances in DV. Actually.
That's great. So Mike, that is I wanted to ask you about the ecosystem and what can the ecosystem or how is the ecosystem supporting reduction of the barriers to RISC-V adoption?
It's a really good question, Ann. I think that the ecosystem is just now coming to grips with this. You know, several years ago, what the ecosystem was trying to do is basically make RISC-V IP available. Well, there's now a collection of RISC-V IP available. Now the ecosystem is struggling with how to disseminate that into a large pool of users. I get a lot of questions about, you know, how can I adopt a certain core and add my own instruction set? So these are the kinds of problems that new adoptees of RISC-V are starting to consider. And, you know, it's only now that you're starting to see the ecosystem address that. And there's several ways of doing it. I mean, Simon talked about Axiomize. Axiomize has got this formal ISA design kit. You just basically, you know, it's a plug and play model, a formal model that will formally verify whether you're compliant with the ISA. Open Hardware has done some work on this in simulation. There's things coming out of organizations like Empirus, but this is, you know, it's still early days, and it'll be interesting to see how it evolves.
Perfect. So Steve, I wanted to ask you about how you're looking at, you know, with the new design freedoms of RISC-V, obviously processor verification is becoming a very big task for all SoC adopters. How do you see this playing out today in DV teams?
Yes, it's I think it kind of takes just a little bit of evolution from what, and I especially kind of latch on to what Simon said about multiple tools. You know, a lot of these methodologies are already, you know, very much involved in part of our IP teams, you know, emulation, formal, simulation, closing coverage. These particular activities don't change all that much, that you're still doing them from that perspective. It's just really an issue of complexity. Although, however, you know, RISC-V does open up a lot of these domain-specific programming kind of paradigms. So, you know, we are tuning our solutions for, you know, to do some particular aspect of one of our IoT SoCs, for example. So it's really just adding a little bit of that layer of complexity to be able to take in a core, kind of understand what we need to, you know, to do with that core. And hopefully by building on some of the tools that are kind of available from companies like Axiomize, OneSpin, their product solutions, Open Hardware, kind of going through this effort, really getting this good foundation of IP put together that we can start to layer on this customization of you know, whatever directions our designers and architects end up wanting to take these cores in the future. And it's more of a delta development than kind of starting from zero.
Right. Other thoughts? Nasser?
I have one more thought. You know, there's, Steve put something, we have all these things already. Every company has their methodologies for doing that. But RISC-V has opened up a wide paradigm of more people having to work together. You know, we can bring a core, somebody else brings other pieces and all that. So now we have to start thinking about interoperability of all these tools. You know, these are all great tools we have, but they don't work together very well. And things like Empirus is doing and others to have things out in the open is very useful. Interoperability is very much. I'll give you one example. Sci-Fi, we have a simulation framework that we've put in open source, and we're doing the performance model there. And we're telling our customers, it's open source, you can do your performance model and can plug and play with our stuff because we're building a core, you're building memory controllers, other pieces. You know, getting all those together to work together has been difficult. We need to make it easier. So interoperability is key, in my opinion.
That's great.
Yeah.
Other thoughts here, Simon?
Yeah, I mean, I could say, I think this interoperability, I think that, you know, the question is, how is this sort of playing out as well with these challenges? And I think that actually verification is quite hard, very hard, and actually daunting to a lot of people. And a lot of people won't realize the complexities of it and the amount of verification a processor requires. You know, if you bought a core from an ARM or whatever, they'd already done the 10 to the 15 petacycles of instructions tests for you. So all you had to do was the integration of it. And this idea of designing your own processor and adding your own things, you've got to learn a lot more about processor DB. And that's a real challenge. And I think, you know, we try and help with people with training and everything like that. And I think that that's one of the reasons it's very important to make use of existing solutions that people have developed over the last 20, 30 years around, you know, SoC verification and performance analysis around things like System Verilog, UVM, and apply all of these to the RISC-V methodologies that come, because it is a daunting challenge.
So how can that really be come to fruition as far as, you know, leveraging all the tools that are there? I think that's a really important point, because especially for startups that are coming into this, maybe using RISC-V for the first time, they need some really solid direction on how they can use their existing infrastructure. Thoughts there, Mike?
Sure. You know, I'm on record as a bit of a contrarian in this discussion. You know, verification largely is a solved problem. The challenge that the industry gets into is they tend to forget it's a solved problem and they just ignore it, and then find out later once they've got problems in the lab that they should have done some verification. So this is, you know, this is a story as old as time, as old as verification anyway. The industry is starting to wake up to the fact that, you know, there are solutions out there. We need to apply them to RISC-V in the same way that we would apply them to something, say, like a PCI Express endpoint or a DDR4 memory controller. Really is the same tools, same methodologies that will provide the same high quality silicon. And there is no magic bullet. It's a, you know, verification is mostly about grinding of the details, and there's no magic bullet to get away from that. So I think this is just a natural part of the evolution. The RISC-V community is, you know, and I think has been for several years now, have woken up to the fact that, you know, it's just a lot of work. You just got to do the work.
Mm-hmm. Steve, do you have any thoughts on this?
Yeah, I'll be a fellow contrarian with Mike. There is no shortcut to really, you know, finishing something out, and I hope the leverage helps a lot. I'll do a little bit of a plug for our work at Open Hardware. I think it'll be, I'm really quite curious to see when folks kind of see the release of our core, see all the work that went into it, all the cycles and tests that it kind of took, and then also try to replicate our coverage reports and results. Yeah, I can tell you from personal experience and you know, maybe some lack of sleep that there was no, you know, shortcut to doing this. There's a lot of work to grind out those corners and figure out if this state transition really needed to happen or not. When, you know, 2 interrupts were occurring and a wake up event, you've got to worry about all that stuff. And you know, having just lived through that, I hope some of the exposure and the openness that we have in replicating these solutions will be something that'll kind of wake up folks. And then also kind of draw them to us to, you know, see what work we've got and kind of build and hopefully contribute to the foundation that we're hopefully developing here.
And if I can just sort of follow up on that one, you know, you guys, I said that I thought verification was a daunting task, and you asked what could be done to help. And actually, I think one of the interesting things that this Open Hardware group has been doing with their funding from their members and the collaboration is this idea of having an industrial quality RISC-V core as open source. But the verification environment is the sort of state-of-the-art commercial style verification environment, which is available as open source that you can download. Sure, you need your Verilog tools and things like that, but it is absolutely the state-of-the-art currently, and you can download it and use it and see the verification quality. So if you make changes to the core because it's open source, you've got out of the box a really high quality verification environment. And I think that's really new, a new concept, an open hardware, not the organization, but for open source hardware, that's a new concept. And I think that this Open Hardware group approach, focusing on the verification and delivering open source core, that's new news. That's a really good idea, which can actually make it less hard for people to adopt RISC-V and validate their processes.
Great, good.
I have 2 comments on that. I agree there's no magic bullet, but I think we need a lot of bullets, maybe a bigger gun.
I'll buy that.
And the thing is, we need our verification environments to be now more scalable, because we are doing much more complex processors now. We have prefetchers, we have branch prediction, we have all kinds of things. And we have to get to a point where maybe we can put system software to do some of our verification, which is very hard by itself. You know, that's why I plug the hardware hybrid emulation simulation solutions. And I'll give you one example that brings it up. Branch prediction. Let's take an example of that. You've got these branch history tables that fill up. You know, mostly in verification, we check to see if it works, but we never check the limits of it. And in my former company, we got a situation where after we ran stuff on silicon for a few days, the performance started dropping. We couldn't figure out why. So we rebooted it and came back. Okay, it's a small bug somewhere. But this happened consistently over time. And after we did a simulation emulation solution, what we found out is when the branch history tables were filling up, it got stuck at the top. Just stuck at thing. And we never got to that point because there's so many numbers without having people run more bigger applications longer, faster.
Yep, yep.
So the scalability is very important.
Yeah, and we've come across that too in previous companies, not RISC-V, but where they were shipping an OS, and we found by simulating the whole thing, actually they had a bug in the scheduler, so things weren't running as efficiently as they thought they were because the scheduler wasn't doing what they expected. But it was only because our tools could monitor what was going on in the scheduler. It just looked weird, and when they looked at it, that's where their performance problem was. And so yeah, it's not just about the gates, because that's sure a challenge in the verification, but it's actually, does the system perform and meet the goals? And for that, you need much more than just a breadboard or last year's product or whatever it is. And you need to go, and this is why for high-end cores, people have huge farms of machines and large emulators. But you don't need that for everything. You can do a very simple RISC-V, and you can get pre-verified now. Cores from people like Open Hardware, where they've done a lot of that verification, just like you would do if you were buying the IP from somebody. So I think the world is changing, but you still got to, when you build these systems, you got to worry about the verification functionality. But as NASA says, absolutely the performance.
So you hit the nail on the head when you said you have to have the visibility. We need instrumentation. Whatever tools we have, we need instrumentation so we can see what's going on.
Yeah.
Much more detail.
Yep.
Yeah, that's a key consideration for sure.
Good. So I also want to talk about the application scenarios. As these become more diverse, what kind of advice can you give to our audience about how to validate the designs in light of the application scenario? Because the days of using small focus tests may not be enough. Where do we go from here?
I'll try to jump in on that. That's a really good question. I'm going to use the RISC-V ISA as a thought example. One of the reasons why RISC-V is so successful is because the RISC-V Foundation, they nailed the instruction set architecture. They nailed the interface between the hardware and the software, right? Getting that right, that's no small feat. And that's why RISC-V is, I believe, one of the reasons why RISC-V has taken off. If we're going to come up with architectures that have to interact with a bunch of novel application layers, we need to do the same thing that RISC-V did. We need to nail that interface between the application and the low-level parts. I'm not saying that that's an easy thing to do, but that's, if we're going to be successful in the way that RISC-V has been successful, then that kind of innovation is what needs to come in. Otherwise, we're going to have to validate everything at the application level every time, and that doesn't scale.
Yeah, I could answer a little. I'm not sure it's an exact answer to the question because it's not really verification, but one of the things that we do in Empirus is we build simulation models of RISC-V, but we do it in such a way that it really scales. And in the sort of modern application area of machine learning and AI, there's a lot of challenges in, have you got the right number of cores there? Have you got the right configuration of the vector engines to do the machine learning algorithms? Do you have the right array with the right communication? And we build technology around simulation, and we can actually layer it up. And we have several customers that have actually done systems with hundreds of high-end cores. And actually, I'm at this conference on it where I actually show some of that. And where they're doing this machine learning stuff with lots and lots of vector engines, lots of vector cores. And so I think that you can help analyze how your application is going to run by doing simulation early. You can often do simulation of a system a year before you commit the RTL on a large project. We've got customers doing that, have hundreds of cores running their full machine learning frameworks and algorithms on it. And yeah, it doesn't run fast because there's an unbelievable amount of competition. I think the AlexNet's a a billion max or something like that for frame or whatever it is. You know, it's a huge amount of computation. But with the type of simulation, you know, if you start early, you can get your applications running way before you make the commit to the RTL. And so I think you can help. I don't know if that answered your question, but you can help in the application space, you know, by using simulation.
Do you have any thoughts here?
Sure, yeah, and I'm coming from a little more of the embedded spaces where, you know, we play, obviously, and I really, you know, echo what Simon says. You know, engaging with simulation, you know, really and from a modeling and kind of architectural perspective is really critical. Getting those software guys, architects, software folks, architects engaged early is really helpful. Again, it's kind of a similar paradigm to just general IP programming models for us. In a lot of cases, it's making sure that we're testing the core or the IP as much as we can, the same way that software is, of course, adding all of our little random hooks and noises and all those kind of things we like to add to it to make sure that we are really covering the cases and using the core and the IP the way the software folks will.
That's great. So I wanted to take just these last couple of minutes and ask for some high-level advice for the system architects and getting into RISC-V for the first time. Top three. Steve, you want to start?
Take advantage of the infrastructure and the ecosystem we've already got. You know, grab cores, throw them on FPGAs. That certainly happened at Silicon Labs long before the hardware RTL guys were ever involved. I mean, there's a lot out there, and there's a lot that you could learn from the tool chain perspective. I also think, you know, leverage what is out there. There's what we're doing at Open Hardware from a verification perspective, and there's things you should be able to replicate within hours, if not less, and kind of look at what we're doing. And yeah.
Great, thank you. Mike.
I'm gonna do a little pitch here. The RISC-V reader. I bought this book 18 months ago. It has not left my desk in 18 months, and I need a new one because it's starting to get too many coffee stains on it. So seriously, that's a pitch for, there's a lot of information out there in the ecosystem. Go find it and absorb that material because it's very good. It's not just the RISC-V reader. There's a lot of other great stuff out there as well.
Great, thank you. Nasser.
So I came from several big companies, Motorola and Samsung. So we had a wide variety of tools, very established tools, lots of money to spend on the tools. So coming to the RISC-V, Sci-Fi world and RISC-V and looking at the tools and saying, this is different. But I was pleasantly surprised. I was very surprised. I'll give you three things there. First, Verilator. Verilator is open source, Verilog simulator. It turns out to be very fast and very nice and very useful. Second, Farson, the FPGA-based emulator that comes out of UC Berkeley, fantastic. I've been able to build my designs much earlier than I've had at Motorola or Samsung. And third, the open source simulation framework we put out, Sparta, which is out in open source. You can do performance modeling and functional modeling, and they can work together. So those are my three things.
Thanks, Nasser. And Simon.
Yeah, I mean, I think just sort of to wrap up, really, I think, you know, the ecosystem plays a very significant part in the evolution of RISC-V, and clearly the verification ecosystem. I think there's a design ecosystem around the IP, there's a software ecosystem around the OSs and Linux and tools, but there's also this verification ecosystem. But and you know, we're all working very hard to evolve that. But also, RISC-V International has something to play, as a key part to play. And things that it needs, I believe, to focus on. One is the specifications to ensure they're tight and clear and can ensure that everybody is understanding the same thing. And the other is this compatibility and architectural compliance that they've got to do, because it's essential that we don't get fragmentation out there, that we can make use of the tools, make use of the compilers, make use of the software. So I think that the ecosystem can do a lot, and RISC-V International and the members can do a lot to help the vibrance of RISC-V and it to evolve very successfully.
Great. Well, with that, we are out of time. Thanks to all of the panelists. This has been a great discussion. I know we covered a lot of ground. But to the audience, please continue to ask some questions in the live chat, and then also watch for the Meet the Speaker session. And thank you very much for attending.
Thanks for having me.
Thanks for having us.
Yeah.